Example 1 here on differential equations is taking a look at finding a general solution to a differential equation. So here we want to find the solution to dy by dx equals 24y squared times by sine x. So here what we need to do first is identify what we're going to divide or multiply by here. Well, if we notice here, if we treat dy by dx as a fraction, what I can note then is this y here in the numerator tells us that on the left hand side of our differential equation that will be in terms of y only, and then the denominator here of this x tells us it will be in terms of x only on the right hand side. So this y here corresponds to this 24y squared. So the first thing we need to do here is divide by 24y squared on the left hand side and the right hand side. So in that case we get 1 over 24y squared dy by dx, and this is equal here now to sine x. Now remember, we want the left hand side here in terms of y and dy here only. So in that case what we need to do now is multiply by dx. So what we get now is 1 over 24y squared dy is equal to sine x dx. Okay. And what we've got here now is a form where we can integrate the left hand side here and the right hand side. We might find it easier to express the left hand side here in the form 1 over 24y to the minus 2 here. Okay, is equal to sine x dx. And here now, all we're going to do now is simply integrate the left hand side here and integrate the right hand side. So we integrate the left hand side and we integrate the right hand side. So here, if we're integrating the left hand side here, well, 1 over 24 times by y to the minus 2, if we integrate that here with respect to y, in that case we're just going to simply add 1 to the power and divide by the new power. And that's going to give us minus 1 over 24 times by y to the minus 1 here. Okay, so that's my left hand side here, that's the result of that integral. And this is going to be equal now to the integral of sine x, and if we integrate sine x here with respect to x, we get minus cos x. Okay, and for this right hand side here, don't forget our constant of integration. Now here, as this is minus 1 over 24 y to minus 1, and we have a minus cos x here, simply all I'm going to do now is just times through by minus 1 to get everything positive. So therefore we get 1 over 24 y to the minus 1 is equal to cos x plus c. Okay, and we're going to keep the plus c as positive here because remember this plus c here is an arbitrary constant. So even if we times it by minus 1, it still remains that it's an arbitrary constant. So in this case here now, 1 over 24 y to the minus 1, well we could write that as 1 over 24 y. Okay, and this is equal to cos x plus c. Okay, now what we want is we want this equation to be in terms of y. So we want y equals some expression. So therefore, what I'm going to do here is times through by 24y. So that's going to be 24y times by cos x plus c. However, what I'm going to do then is divide by 24 lots of cos x plus c. So just get it in terms of y only. Okay, so therefore, y here is simply going to be 1 over 24 lots of cos x plus c here. Okay. Now here, all I'm going to do is finally simplify our denominator here and just expand this bracket here. So y is equal to 1 divided by 24 cos x. And again, this 24 times by c, we wouldn't write this as plus 24c here. We're just going to write this again as plus c here. Because again, this c just represents an arbitrary constant. So again, if we times it by 24, it does not change that it is an arbitrary constant there. Okay, so y equals 1 over 24 cos x plus c gives us the general solution there to our example 1 for differential equations. Example 2 here on differential equations is taking a look at real life problems. So the population P of a herd of sheep increases according to this differential equation. T is measured in years and there's 15 sheep at T equals 0. So simply all we want to do here is find P in terms of T. So let's just denote this differential equation here. So dP by dt is equal to 0.2p. So again here we need to identify which variables are going to go on which side of this differential equation. And again, if we just take a look at the numerator here, and again let's do this in a different colour pen, as the p is in the numerator here, if we treat this differential equation here, this dp by dt as a fraction, well in that case that means the p's will be on the left hand side of this differential equation, and everything here in terms of t will be on this right hand side. So first all we're going to do here now is divide through by p. So therefore, if we divide through by p, we get 1 over p dp by dt is equal to 0.2. And here, again, what we need is just this left-hand side to be in terms of p only, and then dp here. So in that case, we need to multiply it by dt here. So we get 1 over p dp is equal to 0.2 dt. Now it's worth mentioning, you can go straight from this first line here to this last line here, doing it all in one swift action. That's absolutely fine as well, but just to reiterate the steps that we're doing here, I'm going to include the extra step in the middle. So in that case now, what we've got here is the left hand side here, which can be integrated, and then the right hand side can also be integrated here. So if we integrate the left hand side here, we're going to be integrating 1 over p with respect to p, and if we integrate the right hand side here, we're integrating 0.2 with respect to t. So in that case here, the left hand side here, if we integrate 1 over p with respect to p, will simply give us the natural logarithm of p. Okay, and the right hand side here, if we integrate 0.2 with respect to t, will give us 0.2t. Don't forget our constant of integration. Now here, what we want, remember, is p in terms of t. So we need to get rid of this natural logarithm here. And remember, to get rid of the natural logarithm, we take the exponential function of both sides. So in that case, that simply gives me p here on the left hand side, and for the right hand side we get e to the 0.2t plus c here. Now here, this right hand side, we need to use the laws of indices. In that case, we can write p as being equal to e to the 0.2t times by e to the c here. Okay. Now, as c is just a constant, remember, c is just a constant integration, so it's just an arbitrary constant, what that means then is that e to the c will also just be a constant. Okay, so what we're going to do here is call e to the c as a. Okay, so call e to c as a. So in that case, what we can do now is rewrite p here as being equal to a, which is my e to c, times e to the 0.2t here. Okay, so ae to the 0.2t. What I want to do now is use our boundary conditions here. So the idea that there's 15 sheep at t equals 0. Okay, so at t equals 0, we know there's 15 sheep. So that means p is equal to 15. So therefore, what we've got here is 15 is equal to a e to the 0.2 times t, where t is equal to 0. So that's 0.2 times 0. So what that gives us is ae to the power of 0. And remember, e to the power of 0 is just simply 1. So what we get here is that a will simply be 15. Okay, so a is simply 15. And now if we go back to our original equation here, for p equals ae to 0.2t, then we can write p. So therefore p is simply equal to 15a and 0.2t there. Okay, what we've done there is we found p in terms of t there. Okay, so that gives us the solution to example 2 there.